Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're very pleased to have Noga Alon from Tel Aviv University, the IES, and also Microsoft Israel as our first Schramm-MSR lecturer, and he will be telling us about random Cayley graphs.
Thanks. Okay. Okay. Thanks. It's a pleasure to be here, and let me thank you all for coming. And it's actually a special honor to give this inaugural Schramm Microsoft lecture. Clearly, there are people in the audience who knew Oded better than me, but I knew him pretty well since the time he was a student in Israel. In fact, in my first year in Tel Aviv University, I shared an office with Oded's uncle. And he was telling me already there some wonder stories about Oded, who was at that time a beginning undergraduate student. And later, of course, I met him in Israel and in visits in Microsoft in Redmond here. And I want to tell you one story about Oded, and this has essentially nothing to do with mathematics, but still I think it's a nice story. So this was in Microsoft. I was visiting here in one of the summers, and in some weekend they organized some sort of a family day, where the employees of Microsoft Research and their families and visitors went to a park nearby. And there was food, beverages, and then some recreational games. And one of the games was some sort of competition. And it went as follows. So we were partitioned into groups of 7 or 8 people. And then each group got like a big hoop, like a hula hoop. And we were supposed to stand and stand in a row and hold hands. And then you are supposed to pass the hoop around the body of everybody while still holding hands. You probably get the picture, but I have it here anyway. So it's something like this. And if you want to see the hoop better, well, of course, I didn't draw it, but you can imagine that it goes over the hands of these people. And you are supposed to try to do it as fast as possible while holding hands. And I think the rule was that the first one was allowed, after he finishes his part, to help the others. So to stop holding hands with the second guy and to help the others because they were children and so on. And you know that mathematicians can be competitive. Some can be more competitive than others. In short, we really wanted to win. Okay, so we took it seriously. And I was the first one in my group. And I thought that I passed this hoop around my body pretty quickly. And then I jumped to help the others. But while doing so, I kind of glanced at the other groups to see what's going on there. And I was amazed to see that Oded's group was about to finish. We were like in number 2 or number 3 among the 8, and they were more or less finishing. And the reason this happened, so he was the first in his group. And what he's done is that he placed the hoop on the grass, actually like you see here. And then he had everybody kind of going through the hoop while they are still holding hands. And this is consistent with the rules. And you can check it. It's really, you can do it much, much faster than to really take it around your body. And if so, they won by a huge margin. If you think what this shows, so he had the ability to think fast, to be original and think in a non-conventional way. It shows that he has a good geometric intuition. In short, maybe it does have something to do with mathematics after all. I was very impressed, so that's the story. And in the remaining time, let me go to the more technical part of the talk. So here is the title again. So the title is Random Cayley Graphs. And as the three words of the title indicate, there will be here a probability and algebra and combinatorics. And I should point out that already in the first slide there is something inaccurate. Anoop already asked me about it. So the Petersen graph that you see here is not a Cayley graph, in fact, but we will, you can wonder if it's a random graph or not, but indeed we'll want to see something about the difference between Cayley graphs and just regular graphs, maybe. And one of the themes I want to try to convey is that random Cayley graphs is a class of random graphs that is good to investigate, maybe is interesting. Now I wrote here the definition of a graph, not because I think you don't know it, but just to set the notation. So all my graphs will be finite and undirected. I denote a graph G by a pair VE. V is a set of vertices. E is a set of pairs. These are the edges. And a graph is a Cayley graph if the vertices are all the elements of a group, finite group in our case, because we'll talk about finite graphs. So the group is H. And then we have a subset, S, of the group that is closed under taking inverses. So when X belongs to S, then X to the minus 1 also belongs to S. And then two vertices, A, B, two group elements, are connected to each other if A times B minus 1 belongs to S. Or in other words, if one of them is obtained from the other one by left multiplication by an element of S of the set. And here you see an example. The group is the cyclic group with 5 elements, additive group here, and the generating set, or the set S, consists of +2 and -2, right? So we get a cycle. And as I already mentioned, this class of random Cayley graphs, maybe it's interesting to study. And I just remind you here, again, we don't need to do it in this audience, but let me do it anyway, that random graphs have been very successful so their study really is interesting, and there is a lot of systematic study. And it started with a binomial Erdős-Renyi random graphs initiated by Erdős and Renyi and by Gilbert, and some 50-something years ago. And then there are other models of random graphs that have been studied quite a lot. So these are random regular graphs, small world networks, random leaves, and others. And I want to try to convince you that random Cayley graphs are also interesting. Now, definitely random Cayley graphs have been studied, some properties of them, but maybe not in a systematic way as did the other classes, and maybe it's worthwhile to do it. But today I'll demonstrate it only by focusing at one property of random Cayley graphs, and I'll try to give you some motivation for doing it. And this will be the chromatic number. So as you know, the chromatic number of a graph is the minimum number of colors required to color the vertices of a graph so that adjacent vertices do not get the same color. And here you see that the chromatic number of the Petersen graph is 3. That's a proper coloring. And of course, it has odd cycles, so it is not too colorable. Incidentally, whenever something does not make sense, or you want to ask something or make comments, then please do so. So we don't have to wait to the end. Now I want to start with this study of the chromatic number of random Cayley graphs with a motivating question. And this is supposed to indicate that things here are a bit unexpected. So I think it will be hard to guess what's going on. So here is a question for you. So suppose n is bigger than 10 to the 10 to the 10 to the 10. That's the largest number I know to write in a PowerPoint. So this is so n is just a big number. Okay, so it's think about a fixed big number. And we take a group H, and it's of order n. So finite group, n elements. And S is a random subset of H of size, so still big, but small compared to the size of the group. I wrote here 10 to the 10. And we take the Cayley graph of H with respect to S union S minus 1. So I want to have an undirected graph, so I add the inverses if I need them. So this will be a regular graph of degrees, the cardinality of S union S minus 1, so roughly 10 to the 10, or maybe twice 10 to the 10. And we ask what is the typical chromatic number of this graph. Okay. Is it, for example, bigger than 10? So this will be a regular graph. Maybe one thing that we can think about is random regular graph. A random d regular graph has chromatic number about d over log d. Some more precise estimates are known, so somewhat pretty big. And here are some answers here. So with high probability, it actually depends on the group. And here are 3 examples. So if the group is an elementary abelian 2 groups, so just binary vectors of length k with respect to binary addition, then with high probability, the chromatic number will be 2. That's easy, in fact. You can think about it. But the next 2 are less obvious. So if H is a cyclic group with p elements, let p be prime, although it's true also if it is not prime. But then with high probability, the chromatic number will be 3, exactly. So with high probability here, I mean, it's finite numbers. So with high probability, it means with probability at least 99.9%. Okay, let's say. And then if H is a more random-looking group, like a modular group, so SL2ZP, 2 by 2 matrices over a finite field with a determinant 1, then the chromatic number, I don't know what it is, but it's definitely big. So it is certainly with high probability, it is bigger than 10. Okay? And here is another one, another specific example. So let's take again the elementary abelian 2 group. I think that's kind of the simplest group that we understand. So just binary vectors, here of length 1,000 with respect to binary addition. So 2 to the 1,000 vectors of length 1,000. And we take, in this example, 2,700 random elements. Here we don't have to add the inverses, right? Everything is an inverse of itself. So this will be a 2,700 regular graph, the Cayley graph. What is the chromatic number of the Cayley graph here? So here it turns out that, again, with high probability, so at least 99.9%, the chromatic number is exactly 4. It will be exactly 4. And I thought that's remarkable, so I added an exclamation mark, and then I saw that the 4 looks like 4 factorial, so I dropped it 1 line below, but this is okay. So these are examples, and of course you can guess the general question, and I should say that despite what these examples may indicate, really we know very little about this question. So these were the few specific cases where we kind of know the answer, but usually there will be a very big gap between upper and lower estimates. So the general question is that H will be a given finite group. So someone gives you a group, think about your favorite group, and S will be a number, say, between 1 and H over 2. It's not so important. And we'll take a subset S of H random, uniformly at random. So this will be a subset S of cardinality little s. We add the inverses, and we look at the corresponding Cayley graph. Okay. And we ask what is, so now the chromatic number of this Cayley graph is a random variable. We can ask about the distribution, right, expectation, variance, whatever, but we are very far from trying to understand really the second moment. So I just want to understand the expectation, or just to get what is the typical value with reasonable probability. Okay? So this is what what we'll want to know. And in some cases, we'll be able to say something. And in some cases, we'll not be able to say much. In fact, there is no finite, there is no infinite family of groups for which we know really the behavior of this chromatic number for all the ranges of the number of generators of the cardinality of S. So this will be interesting to understand even for elementary abelian 2 group or cyclic group of prime order, whatever. Now let me talk a little bit about the motivation. So I'll mention 3 things. I'll do it quickly. So here I'll mostly mention the buzzwords. Again, you can stop me if you want to hear more, or I can. But I think so. This gives reasonable motivation for trying to understand how the chromatic number of random Cayley graphs look. And the first one is maybe the connection to expanders. So expanders are, again, as probably most of you know, are very sparse graphs that are very highly connected. So the degrees are relatively small, maybe constant, or maybe small compared to the size of the graph. But every small set, every set of most of the elements expands in the sense that it has lots and lots of neighbors outside the set. So these are expanders. And the best constructions of expanders, and you can say so at least the best in terms of the spectral gap, are Cayley graphs. So this holds for the Lubowski-Phillips-Sarnak-Ramanujan graphs, found also by Margulis, and this is true for many other constructions as well. So these are Cayley graphs. Why random? So it turns out there is something quite general that we proved with Reuchmann a long time ago, that for every finite group that you take, if you take, say, 2 log the size of the group random elements, then with high probability, this will be a good expander. Okay, so really random Cayley graphs tend to be expanders. And in fact, if the group is more carefully chosen, so these are more recent results by Bourgain and Gambord. So for example, for SL2ZP, 2 by 2 matrices over ZP with determinant 1, even if you choose a bounded number, so 10 random elements, then with high probability, this will be an expander. And something similar holds for other groups. So I just mentioned here this paper by Brouillard, Green and Tau. This is for Suzuki groups. So basically the same kind of machinery works for many other groups. So it means that random Cayley graphs tend to be expanders. Now you see, an expander, if you are really a very good expander, think now about degrees that are somewhat bigger than constant, then you cannot have a big independent set, because a big independent set is a set so that all the neighbors are outside the set. So it means that it doesn't have so many neighbors, because it doesn't have neighbors inside the independent set. In fact, being a very good expander is essentially like saying that you don't have big independent sets. And for Cayley graphs, in fact, for any vertex transitive graph, saying that the largest independent set is small is essentially like saying that the chromatic number is large. There is some logarithmic gap between the 2 obvious bounds, but it's essentially the same question. So somehow understanding the chromatic number of random Cayley graphs is closely related to understanding their expansion properties. So this is one. The second one, I'll also not say much. So this comes from information theory. And just to say it without explaining the word, I'll say something about the Witsenhausen rate soon. So it turns out that random self-complementary Cayley graphs provide examples of graphs with large chromatic number in small, what's called Witsenhausen rate. So that's in an old paper with Alon Orlitsky. And let me describe to you what is the problem here. So this has something to do with communication complexity, communication game. So think about the following communication game on a graph G. So we have the 2 parties, Bob and Ellis, as usual. And they know a graph G. So G is some specific graph that they both know. And then Bob knows an edge of the graph, and Ellis knows one of the endpoints of the edge. Okay? And what they want is that Ellis is trying to, maybe it's written here. So Alice is trying to send a small number of bits to Bob so that he will be able to tell which endpoint he has. And this is just a one-sided communication problem. So she's sending the bits, and then Bob is supposed to know which side he has. And you ask how many bits she has to send. And that's actually simple. So if you think about it a little bit, you see that what she really has to send, and that's the minimum she can do, well, since we are counting by bits, she has to send log base 2 of the chromatic number of G, ceiling, let's say. Because what they can do is they can agree on a proper coloring of the graph, and then she will just send the color of her endpoint. And because the two endpoints have different colors, then Bob will know. And this is if and only if you can convince yourself that if they have a good protocol, then for two adjacent things, she cannot send the same information. So she really has to send bits that correspond to a proper coloring of the graph. So that's a question that is well understood. But one of the main themes in information theory is that things often become more efficient as the length of communication increases or as you repeat things many times. And this is what we want to ask here, and this leads to this notion of Witsenhausen rate. It's like some analog of Shannon capacity to those. So what Shannon capacity is for independence number, Witsenhausen rate is for chromatic number. So let's ask ourselves what happens if Bob has two edges, E1 and E2, and Alice has an endpoint of E1 and an endpoint of E2. Now she wants, again, to send to Bob bits, and bits that will enable him to reconstruct both endpoints. And the question is, can she send much less bits? So of course she can do what she did for one case and double it, doing it twice. But maybe she can do better. Maybe what's called the direct sum thing fails here kind of in a strong way. And indeed, it turns out that sometimes she can gain a lot. And if you take random, so some model of random self-complementary Cayley graphs of high chromatic number, they provide examples where the number of bits in both cases will be about the same. So even for doing it once, Alice will have to send roughly log the number of vertices bits. But for doing it twice for two completely independent things, she would still have to send the same, maybe plus 2 or something. Right? So what she had to send for one, plus another bit and a half or 2 bits or something. And if you do it many times in the limit, when Bob has many, many edges and Alice has many endpoints, and you ask what is the number of bits she has to send, and they pair edge, so you divide it by the number of edges, then it's not difficult to see that this thing has a limit, and the limit is called the Witsenhausen rate. And there are several interesting questions regarding the Witsenhausen rate. So as I said, these random self-complementary Cayley graphs, they provide examples where one edge will require roughly log n bits, and the Witsenhausen rate, so in the limit, it will drop to about half log n. But it's not known, for example, if there are graphs on n vertices where for one edge you have to send roughly log n bits, namely the chromatic number is roughly n, or n to the 1 minus epsilon, and still in the limit you will have to send only, say, 0.01 log n bits. And just a minute, and maybe understanding these random Cayley graphs and the behavior of the chromatic number better will tell us something about this. There was yeah, so self-complementary is isomorphic to the complement. And the complement is replace every non-edge by an edge and every edge by non-edge. Okay, so this is now there is a third motivation that comes, this was my original motivation actually, and that comes from additive number theory, and I think it's an interesting question. So this has to do with sumsets. So in additive number theory, really a lot of the work is about sumsets. I checked last week, so in MESSCI.NET, there were 163 papers with the word sumset in the title. And there were actually 53 more papers with the word sumset in the title, but there it appears sum and hyphen set. So there are so really this is studied a lot. So what is a sumset? It's just you have a set A, and you look at the sum A plus A. So the sum of all little a plus little b, where little a and little b belong to A. You take all the sums of pairs, and you want to understand the structure, or how does it look, what sets are sumsets. And one thing that was discovered by Ben Green, and it's quite surprising, that if you are in ZP, so in the finite field with I mean here it just says an additive group, and it's a group with p elements, then every complement of small set is actually a sumset. So if you take all of ZP and you omit 100 elements, no matter which 100 elements you omitted, if P is big enough, then this will be of the form A plus A for some appropriately chosen A. And it's natural to ask, and he asked actually what is so let's define f of b. F of p will be the maximum number f, so that whenever we delete from ZP a set of f elements, then what we get is a sumset. Okay, always. And we want to estimate it. And he showed that it goes to infinity with p. So really this f of p is at least 1/9 or something times log p. And with Gowers, they showed that f of p is at most some constant p to the 2/3 plus epsilon, so a little bit. I could improve the bound. So really a lower bound is something like square root p over square root log p. Whenever you delete square root p over square root log p elements from ZP, it's always a subset, what you get. And the upper bound is at most p to the 2/3 over some logarithmic power. But the truth should be, so there are several reasons to think that the truth should be roughly p to the 1/2. Okay, so the lower bound should be closer to the truth. And let me tell you something about how the proof of this upper bound goes, because this is what I think that one should improve, and why is it related to this chromatic number of random Cayley graphs. So roughly it goes as follows. We have to show that we can choose a set B which is not so big, right? Maybe p to the 2/3, so that the complement of it is not a subset. So we just do it in 2 steps. We choose B as a union of B1, or did I write here B and B prime? A union of B prime and B double prime. Okay. So first we choose B prime, half of the elements of E, and we say that, okay, these all are going to be in the set B that I'm trying to construct its complement as a subset, or to show that its complement cannot be a subset. Now you see, once I know B prime, then any set A, so that A plus A would be ZP minus B, A plus A has to avoid B prime, because B prime is part of B. Okay? So it means that A has to be an independent set in the Cayley, here it's Cayley sum graph, but some graphs are really similar to a usual Cayley graph. So instead of difference, we take sum. 2 are adjacent if their sum belongs to B prime. So A will have to be an independent set in this Cayley sum graph with respect to B prime. Now, if all these independent sets are small, then there aren't too many of them, just because there aren't too many small sets. And therefore, now, since I can complement B prime to a set B by many ways, I can just add another set of the same size, roughly, and I can do it in many ways. If there are more ways to complete B prime to a set B than there are potential A's, then this will give us some B that is not a subset. So that's basically how it goes. And the main thing you have to do is to show that indeed there is a choice of B prime, which is not so big, so that the independence number of the Cayley sum graph is small. I already told you that for Cayley graphs, independence number and chromatic number are about the same. Well, here it's a Cayley sum graph, but it's still roughly essentially the same. And somehow to So if we would be able to understand, I think, what is the typical chromatic number of a random Cayley graph, it will be the same as a random Cayley sum graph of ZP with respect to about square root p random elements, then hopefully we will be able to prove this square root p in that question of green. Okay, so these are some. So let me tell you what is known about this question, what is not known. So here is the notation. H will be a group of size n, just because G is the graph, so H will denote the group, and S will be a random subset of size k, which is at most n over 2. It's not so crucial here if you take k distinct elements or you take them with repetitions, because the gap between the bounds is larger than the difference between these two models. So think about what you prefer. And let me denote by this chi of hk the chromatic number of the Cayley graph of H with respect to S union with the set of its inverses. And of course, it's a random variable. We want to know what is its typical value. So here is the comments that I already said. That of course, this is a regular graph, as is every Cayley graph is regular, it's vertex transitive. The degree is roughly k, right? So it's at most 2k, because maybe we took k elements and we added all the inverses. Maybe there were some repetitions, or maybe some are inverses of themselves, but the degree with high probability is essentially k. And therefore, just by the trivial upper estimate for the chromatic number of any graph, then the chromatic number is always at most this degree, plus 1 if you want, or since if it's not a clique, then you don't need the plus 1. And a known fact that I mentioned is that the chromatic number of a random regular graph of degree d is roughly d over log d. So maybe one guess would be that here it should be close to that, although I've told you at the beginning some examples where the behavior was a little bit different, but still, in fact, I suspect that for bigger case, this gives kind of the right behavior. But this could be one guess, and here are some results. So here is something that holds for any group, for general group. You don't assume anything about the group. So the group is just a finite group of order n elements, and k is anything. Then the following estimates hold with a high probability. So the chromatic number of this Cayley graph of H with respect to k random elements and their inverses is at most some constant k over log k. So indeed, you can always gain this log k in the upper bound, the same as what happens for usual k regular random graphs. What about the lower bound? So there is a pretty big gap between the lower bound and the upper bound with high probability. So of course, as always, with high probability, I mean with probabilities that tends to 1 as as the size of the group tends to infinity. Okay. So in the lower bound, you have instead of log k in the denominator, there is log n, log of the size of the group. But what's worse, there is a square root on both the numerator and the denominator. So in general, that's kind of the best lower bound that I know, square root k over square root log n. And notice that the log n somehow has to be there, because I told you, I didn't quite tell you maybe, but the examples that I showed in the beginning for ZP, these were with specific numbers, actually shows that for some groups, really the chromatic number doesn't grow at all as long as you choose randomly only log the size of the group elements. So then still the chromatic number stays 3 or something. But then it starts growing. Okay, so it will come soon again. And another lower bound that is somewhat better if k is big, so if k is bigger than square root n or something, it's always at least some constant k square over n log square n. So in particular, if k is n over 2, if it's really a dense graph, something that looks like the random graph gn1/2 or something, then this will tell you that the chromatic number is at most n over log n because of the first bullet there. and at least n over log square n, because of the second bullet. So at least for dense, one understands it reasonably well. In the middle, there is a very big gap. So in the middle, let's say when k is about square root n. This is here is something, okay, and I should say there's some special cases. So mostly the case that k is equal to n over 2 has been considered before. So it follows from the papers that I mentioned, and there is also a more recent paper by Christofides and Markstrom. So basically the case of k equals n over 2 has been studied. Now here is something about a specific graph. So for SL2 ZP and for other finite simple groups as well, but let's just take SL2 ZP, then there exists some absolute constant delta, maybe 1 over 100 or so that for every k, then if you choose k random elements and add their inverses, then the chromatic number will be at least k to the delta. So it starts growing there immediately. And here is a groups of prime order, so cyclic group of prime order. There is a result by a young Polish mathematician called Czerwinski. So he showed that for k, which is at least log p over log p to the 1/2, so up to some point, then the chromatic number is at most, actually, it's exactly 3, right? It's at least 3 because p is odd, so any element will give you an odd cycle. So, and if k is not so big, then with high probability, the chromatic number is exactly 3. And this can be improved up to k, which is, so this is what the proof gives. I don't know if it stops exactly there. But if you go up to 0.99, say, or 1 minus epsilon log base 3 of p, then with high probability, the chromatic number is at least 3. And because of what I said before, for the lower bound, the log behavior is sort of tight, right? So we know that once the number of elements we choose is significantly bigger than log p, let's say 100 log p, then the chromatic number starts growing because there is this lower bound that is a constant square root k over square root log p. Right? So once, okay. This is for groups of prime order. Something similar holds for any cyclic group, and in fact also for any abelian group. But let me, if we stay with this ZPK, if we choose more elements, so then the chromatic number is at most k over log p, roughly. So we gain this log p, but afterwards maybe we keep growing. This is the upper bound. And for the very dense case, so if k begins to be a constant p, like half of p or p over 100, then there is a result by Green and a more accurate estimate by Green and Morris that says that actually in this case the chromatic number is up to a constant p over log p. So it really behaves like the usual random graph up to a constant. And in fact, for ZP and C equals 1/2, even the constant is a correct constant. So they really behave like random graphs. Okay, so these are results, and let's say something about proofs. And naturally, the proofs combine some probability because we are talking about random graphs. Some algebra because it's Cayley graphs, so specifically there are spectral bounds that are used, so some properties of the eigenvalues of the graphs and the known connection between eigenvalues and the chromatic number, and some combinatorial arguments because this is combinatorics. So I want to show something that is maybe part of the probabilistic part, and it will be a simple thing that I can almost describe. Maybe I'll just say, so this is about groups of prime order. So usually you prepare a PowerPoint presentation, you want a picture, so you go to Google Images or Bing Images, and you type the sentence, and you look at the pictures, and usually you have no idea what's the connection of the picture you get to what you typed. But here I thought about it in the sense that this is a group of people and there is a prime number of them, because this is so I think that's why. But anyway, definitely this is what I got. Okay, so we want to prove, this will be pretty simple. We want to prove that the chromatic number of ZP, cyclic group, P elements with respect to K randomly chosen elements, and K is at most 0.99 log base 3 of P. We want to show that with high probability, the chromatic number is exactly 3. Okay? So we'll do the following. And okay, so what we want to show is that with high probability, if we choose these random elements x1, x2 up to xk in ZP, and k is what we said, then there is an element A in ZP so that A times xi modulo P, all of them lie in the middle third between P over 3 and 2P over 3 for all I. And let me show you why this is enough. It's similar to things that, so probably some of you see it already, but let me show it anyway. So suppose that I know already that there exists such an A. Then here is the coloring. We take ZP and we cover it by 3 cyclic intervals that are nearly equal. So each of them is of size P over 3, at most ceiling of P over 3. Okay. And then we have this A, this element that I'm still supposed to tell you why it exists. And we have to color each element y. So to color y, we take y, we multiply it by A, modulo P, and we see to which interval it falls among the 3 disjoint intervals. And this is the color. If it fell into the second interval, then the color is 2, and if it's a third, and so on. Okay. So why would this be a good coloring? That's simple to see. We have to show that if y1 and y2 have the same color, namely the ay1, ay2 fell into the same interval, then the difference between them is not plus or minus one of our xi's, right? And why is it the case? Because if they fell into the same interval, then the difference between them is smaller than the length of the interval. So it's strictly between minus P over 3 and P over 3, this difference between them, because they lie in the same interval. But all the AXI are in the middle third between P over 3 and 2P over 3. So they are not between minus P over 3 and plus P over 3. And therefore, this difference is not AXI, meaning that the difference before I multiply by A is not XI. And therefore, the coloring is good. Right? So that's very simple. Now, why there is this A? Okay, so I'll say something about this. So the intuition is very clear, right? So you fix an A in this ZP star, so in non-zero element modulo ZP, and then the probability is that AXI, now we take these xi's randomly, the probability is that AXI fell into the middle interval is 1/3 for each fixed xi, and these are random independent, so the probability is that all of them lie in the middle third is 1/3 to the k, and because k is 1 minus epsilon, or 0.99 log base 3 of p, then this 3 to the k is still significantly smaller than p, and because of this, the expected number of a's, which will be okay, is big, right? So we kind of expect to have one. But of course, we still have to prove it, because the fact that the expectation of a random variable is big does not mean that it's positive with high probability. So one has to prove something, and definitely the above events for distinct elements A's are not independent. If you know that A xi is in the middle third, then 2A xi is certainly not in the middle third. So some of them really depend a lot on each other. So somehow you have to use second moment, and there is a nice trick that works only for the prime case, and I just say this trick. So this trick is useful. I think, like, for example, in a paper with Yuval, we used it a long time ago. And I not say why it really, and something is written here, but let's not, let's just not look at it. I'll just say that instead of looking at AXI modulo P, we look at we add a Y. So instead of looking at AX, where X is random, modulo P, we look at AX plus Y modulo P. Right? And somehow, the good thing about adding Y, although it's not clear, it seems unrelated to what we are trying to prove, the good thing about it is that when we add a Y, then for two distinct A's, for A1 and A2, the events at A1x plus Y lies in the middle third and A2x plus Y lie in the middle third become independent. So all these events will become pairwise independent. And if they become pairwise independent, it means that we can compute variance and we can apply Chebyshev. And if we do it carefully, then we realize after a while that the fact that we added Y is not so crucial, so we have to do something, but there is a way to take this Y away. Okay, so this is not supposed to make too much sense, but at least to understand what's going on, and it's not too complicated. It's more complicated if you want to do it for general cyclic groups when P is not a prime, so then but the same result still holds, or if you want to prove something for abelian groups or for okay, something quick about general groups. So this is this very different. So basically, what we know to do there is just to use a spectral connection between the chromatic number of graph and the eigenvalues of the adjacency matrix. And so this is what's written here. So, so one bound that I mentioned is that for any group H of order n and for all k, this chromatic number of the random Cayley graph of H with respect to k randomly chosen elements is at least constant root k over root log n. So the way to do this is to use the following. So this result with Reuchmann that I already mentioned is that for any group, if k is bigger than log n, and if you take k random elements in the group, you can look at the non-trivial eigenvalues. So the biggest eigenvalue is always the degree of regularity in a regular graph. But you can look at all the non-trivial eigenvalues, and one can show that with high probabilities, absolute values of all the other eigenvalues is at most constant root k over root log n. And there are several subsequent proofs of the same results that are somewhat better, so they give a little bit more information. At the beginning, I was very happy to see that people keep reproving it because it shows that they are interested. After a while, I started to think, what's wrong with the original proof? But anyway, so this is so there are indeed some better proofs, and then there is a simple old result by Ehlen Hoffmann that shows that the chromatic number of any d-regular graph in which the smallest, the most negative eigenvalue is lambda, so lambda is always negative because the trace is 0, the sum of eigenvalues is 0, the smallest one is negative. But if the negative one is small in absolute value, so it provides a lower bound for the chromatic number. The chromatic number is always at least minus d minus lambda over lambda. Because lambda is negative, this is a positive number. So you just plug in it and you get a lower bound. And essentially the same works for those other groups. So if you look at what for example, the Bourgain-Gambord proof does, it shows that if you take a random Cayley graph of SL2 ZP with respect to some bounded, or with respect to k generators, then all the non-trivial eigenvalues with high probability will be somewhat small, and somewhat small here is k to the 1 minus delta. So some smaller power of the degree of regularity, and this and again you plug in there. So this would give that with high probability the chromatic number of SL2ZP with respect to k random generators will be at least k to the delta. So let me just use the last 3-4 minutes to mention a few open problems. So there are many problems. Of course, the main one is maybe to close the gaps between the upper and lower bounds. And as I said, there is no even a single infinite family of groups, so say binary vectors, so elementary abelian 2 groups, or cyclic groups, or any groups you want, for which we understand the behavior of the typical chromatic number when, say, the number of generators is square root of the size of the group. So then the bounds will be, the lower bound will be about the 4th root of the size of the group, and the upper bound roughly the square root. There are some logarithmic terms here and there, but just to understand the right exponent. But maybe it's interesting to look at other groups. So, so in particular, I wrote here the symmetric group. I haven't done it much, but I think it's a. Now, it should be true. I don't know to prove it, but it seems that it should be true that for solvable groups, the chromatic number stays small, at least at the beginning. So until k is maybe logarithm of the size of the group. And so this, it seems that it should be true. I mean, as I said, it's true for any abelian group. And if it's true for solvable, then we would know that for every group of odd order, this chromatic number with high probability is exactly 3, right? Because it's, they are always solvable by the Phi-Thompson theorem. For h equals z2 to the t, it seems that this is a group that we understand best. I mean, just binary vectors with respect to binary addition. You can prove there a little bit more than what I said in the, for general groups. So if h is z2 to the t, binary vectors of length t with respect to addition, so if k is n over 2, let's say, we choose half of the elements, then the truth is both upper and lower bounds up to a constant factor. In fact, I think that there you can get even the right constant. It behaves like n over log n log log n. So it's not really like a usual random graph, but there is another log log n factor. And the reason for that is that these groups have very many subgroups, right? So this is a difference between them and cyclic groups, and because of this, you gain something. And what I mentioned at the beginning was a special case of this. So if the number of generators that we choose is between 1 plus epsilon t, let's say, and 3 minus epsilon t, then with high probability, the chromatic number will be exactly 4. So, so the examples that I mentioned at the beginning was z2 to the 1000 when we choose 2700 elements, and with high probability, the chromatic number will be exactly 4. Maybe it stays 4 even a little bit further. I don't know to prove it, but it could be. But we know that after that, it should start growing, right? So once, for any group, if we have some big constant times log the size of the group, then the chromatic number is at least the square root of this big constant. So it starts growing, but OK. And finally, maybe the following could still be true, and I actually believe it's true, that although we've seen that there are some differences between groups, then it seems that these differences are only logarithmic factors. So maybe, and in fact, it could be true that for every group of order n, and for all admissible values of k, this typical chromatic number is equal to k up to polylogarithmic factors in n in the size of the groups. So this is true when k is very small. It is true when k is very big, when k is close to n. But it will be nice to know it for k, which is about square root n or anything in between. So just to understand the behavior when k is a power of n. And this looks interesting. And with this, I'll finish, and thank you for your patience.
Any questions or comments?
Are all the lower bounds via the eigenvalue?
No, so there was a lower bound that I didn't talk about, that for large k, there was this k square over n log n, and over n log square n. So, so this was a different, so it's some more probabilistic counting argument. And again, some of them also use some specific, so this n over log n n for z2 to the t, it's something more specific for the group. But indeed, for kind of the middle range, when the degree is about square roots, then they all come through the eigenvalues, indeed, and maybe. Yeah.
And it's possible that you could get the best lower bounds that you want this way, or is there?
You mean, is it possible that
to close the gaps? Could you still do it
by eigenvalues? No. So the eigenvalues will not give better. This is the correct behavior of the eigenvalues. So because the second eigenvalue of a k-regular graph is always at least something like square root k, and yeah, and here we would need yeah. Mm-hmm.
So number of results were for around n over 2 or so in the where there were many results known. In terms of the other applications, are they things like square root n, or what are the regions of k that you're really interested,
right? Yeah.
Most interesting for that? Okay.
Yeah. So I think, as I said originally, I was interested in this square root behavior because that was related to this question of Green and Gowers. I mean, so this is one range which looks interesting. Yeah, I mean, for the k over 2, it looks interesting because of trying to understand the analogy with usual random graphs, but there the gap is smaller. So I think. And then for small k's, it's interesting, I think, to understand for which groups it stays small as k grows, and for which groups it starts growing immediately. But indeed, for me, square root will be the most interesting. Yeah.
Is there anything you can say in general about concentration of the chromatic number?
Right, yes. So I thought about it. I mean, for the range where I proved that it's 3 with very high probability, I can say something about the concentration as well.
Because if you know the value.
It should, right, so kind of I keep thinking that I should think about it more. But it should be true that it's concentrated, that it's very concentrated, at least when the typical chromatic number is quite small. So I would expect, just because of the analogy with usual random graphs, that maybe whenever the chromatic number is at most even a small power of n, then it's concentrated in 1 or 2 values. But I don't, I don't know. It's it's interesting, I think. Somehow.
Questions? Let's thank Noga again.